I'm going to announce a little program change. They asked me to do 45 minutes and then take 15 minutes of questions. There are never 15 minutes of questions. We always just try to run out the clock. So if I get to the end of the presentation, I'm going to do a little bit on career stuff. Deal? Okay. My name is Steve Switaj. I am one of the heads of engineering at Laika Studios. We're the largest stop-motion animation facility on the planet. This is a presentation about some large characters we built on our last feature, Kubo. We originally gave this presentation at SIGGRAPH 2 years ago, I think. And let's launch. We're playing, right? Do you guys have a... Can we put this up on the monitors? There we go. Really, I could tell you about Laika, but I'm going to let our CEO, Travis Knight, do it for me.
Laika is something of a physical, tactile wonderland. It's really an extraordinary place. I think the air just crackles with creativity and innovation.
When I toured the Laika studio, I was just amazed at, first of all, the size of it, the amount of people involved, the years it takes, and just the level of artistry.
You feel like you're in this factory of dreamers, and everybody's meticulously working on that one small detail with so much perfection and so much dedication. It really felt like I was in a different world.
There's something about stop motion specifically where it's a primal thing. It feels like a child's plaything being brought to life. It's like we're playing with our dolls, playing with our toys, telling stories that mean something to us.
The soul of this type of artwork is really there. You could feel it.
Everything is shot in camera.
Look to the right, please.
There's a real puppet in real sets, and every frame, and there's 24 frames in every second of the film, he's being adjusted and moved, and it takes 3 or 4 years to actually shoot the movie.
Bravo.
What we do at Laika is to take this style of filmmaking, which is craft-based. It's about artists using their hands to bring something to life, and blend that with technologies. We grow in our creative capacity and our artistic ability with every successive film, which means a film like Missing Link, which would have been impossible to even contemplate a handful of years ago, is now something that's taking this beautiful art form to a new place.
The hours of attention, of detail, of lighting, of creating characters and worlds which feel so real, and people imbue so much love and creativity into, because they're spending 5 years of their life with these characters, it has to really matter to them. The movies they make leave you with something very inspiring and heart-filled.
The kinds of stories that we're developing now are unlike anything that we've ever done before. And it's just really exciting. It's scary as hell, but that's how I feel like we're on the right track when we're doing something that fills me with fear, because that means we're probably doing something that hasn't been done before. I feel like we're just getting warmed up. We're just getting started.
So, those of you familiar with Laika will know some of our movies. Our first movie out was Coraline. We did a good job on that, very critically acclaimed. We got a nomination for Best Animated Feature, and of course we lost that year to Disney. And then Paranorman got an nomination for Best Animated Feature, lost to Disney. Box Trolls got an animation, lost to Disney, blah, blah, blah. Our fourth project was Kubo. Now, Kubo was a bit of a departure. We went to make the kind of film that was, if you can imagine a Kurosawa epic, the Seven Samurai, but the samurai are 7 inches tall. That's pretty much what we tried to set out to do. And it's a pretty big film, in scope. I'll show you the Kubo trailer so you can get an idea.
What was Father like?
He was just like you. Strong, funny, and so handsome.
Ugh, Mother.
But you got your magic from me.
I can fly? My name is Kubo. This is my story.
Your enemies aren't far behind. Your magic is the only thing that can protect us. You need to learn control.
Release!
Do you ever say anything encouraging?
I encourage you not to die.
I encourage you not to die.
Don't touch anything.
He did it.
Come on, this way.
You got this. Kubo.
Do you need a little help?
No. Yes.
I love the big wraparound shot of the monkey climbing up the sailboat mast. That was mine, by the way. So the theme of the movie is adventure. It's the standard hero's journey. And our heroes face a great many challenges. But one of the biggest challenges will occur here in the Hall of Bones, where they will meet this skeleton monster, a huge, evil, remorseless monster made of the bones of its victims. It's 100 feet tall. It's based very loosely on the Japanese Odokuro legends, the giant starving skeletons. These things were big, they were evil, they were remorseless, they were reported to be unbeatable. I don't really know who they were reported by who survived it, but at any rate, they were also reported to be, and this is important, 80 feet tall. Now, we do things in puppet scale at Laika. It's roughly a 1/6 scale world. But if you take an 80-foot tall monster and you scale it down by 1/6, you get 15, 18 feet-ish, depending on your art direction. That is, to belabor the point, somewhat bigger than a typical Laika puppet. Now, we try to shoot things practically. I don't want to say we're allergic to CG, we use a lot of it, but we feel that when you buy a ticket to a Laika movie, one of the things you're buying is that stop motion experience, that tactile thing. And we feel sort of an obligation to our audience, and we always try to do things practically if we can. So we were going to do, to the extent possible, a practical skeleton. Now, there's a trick in animation. You shoot small things and you make them look big. Willis O'Brien did King Kong in the 30s. He did not build a 40-foot monster. He built a monster that was a foot tall. Ray Harryhausen, when he did his famous Voyages of Sinbad, he built small skeletons. And we were going to build a small, manageable creature because, frankly, if it's good enough for Willis and Ray, it's going to be good enough for us. So we're not going to build an 18-foot tall puppet because that would be insane. So instead, most of it's going to be shot by a 3-foot puppet sculpted by Carl. Carl for scale here. Or so we thought. At least initially, the plan was quite workable. The puppet worked really well. It animated well. It was about 3 feet tall. The issue was that the character puppets that went with it had to shrink down proportionally, and all of a sudden our hero puppets were about 1.5 inches tall. Although the animators loved the 3-foot skeleton, they were less in love with the little tiny character puppets that had to interact with it. At 1.5 inches tall, we really couldn't put a good armature in here. They wouldn't hold position very well. They were tough to manipulate, and also, like, they were 1.5 inches tall. We weren't really sure that they would hold up. We always knew that we would, for the tight interaction, we would need bigger pieces that the puppets would interact with. We always knew we'd need to build a hand, you know, the top of a skull, sort of that. But as we started testing, we realized that the shots we thought we could get away with our smaller puppets, no, we can't do the monkey and the hand at that scale. We're going to need a real hand and a real monkey, and now we're going to need a real arm. The shots just started adding up. You know, an arm here, a scapula there. We have a cranium where there's an actual sword fight, so we had to build 2 of those. So you start adding things up, you start coloring in the map, and all of a sudden it looks like this, where you realize that everything is that is shaded has come up for discussion needing to be built full scale. Now, those of you who are innocent of the sin of mission creep can cast the first stone. But at some point, there's a meeting, and everybody's looking at this picture, and somebody finally says it. They say, you know, I mean, we're building most of the puppet. Why don't we just build the whole thing? And with that, the seed of insanity gets planted. Now, it's not as crazy as it initially seems because Laika is really no stranger to large puppets. In our previous film, The Box Trolls, we had this creature. This is called the Mechadrill. It's sort of a steampunk Gundam kind of thing. It's maybe the size of a large child. It ended up weighing about 70 pounds. But we managed it. We had 4 or 5 of these things by the time we were done. And it's funny because at the time we told people this was the largest stop motion puppet ever made. And, you know, the fan base begged to differ. They talked about the chicken walker from Star Wars. They talked about the jaguar shrimp from Life Aquatic. So they can bite us because we are going to build this thing for real. And the arguments are going to stop. This being said, this is going to be an entire different league. I mean, the top, from the waist up, the top torso is going to be about 12 feet tall, weigh maybe 400 pounds. We looked around to steal some ideas. I mean, borrow creative inspiration, right? And we are just alone on the field. No one has ever attempted this. Georges Méliès of Earth to the Moon fame actually did have a big marionette creature roughly this size in one of his big epics. But he had 24 men working it with cables, and we don't have that. So we sit around, we figure out how to do this, and we start, you know, reality starts setting in. One of the issues is that unlike some sort of set or prop or statue, this isn't, you know, just something that's going to stand in a corner. It's a performance piece. It has to be fluid. It has to be posable. And that opens a whole new can of worms. Mass becomes incredibly critical. And it goes up with the cube of size. If you take an object and you grow it by 100%, and make no other changes to materials and whatnot, it gets twice as tall. It doesn't get twice as heavy. It gets 8 times as heavy. It goes up by the cube. Now, we're not talking about growing something by twice. We're talking about growing something by a factor of 6. Now, for those of you who don't have a calculator handy, the cube of 6 is 625. For those of you without a hand and feel for math, 625 is a very large number. Inside every animated puppet is an armature made of little bits of steel and brass and nylon, full of exquisitely crafted joints. I really wish I could have brought one of these. They are jewels. They have the perfect amount of drag. They have the perfect amount of stick. We have a CNC shop that does nothing but build these things, and then they get cast in latex and they become a puppet. And their job is to allow the thing to be posable and hold its weight against gravity. The armature can, in fact, cost way more than the rest of the puppet. Whenever I do a presentation and take one of these somewhere in my car, I quadruple the cost of my vehicle. But the joints of such a big puppet have to resist a lot more torque than the joints of a little puppet. And torque, of course, does not scale linearly with size either. And the torque and the drag of manipulating these things is going to be a huge issue. Torque, drag, weight, mass, these are all going to be the critical things we have to work with here. So how do you get this puppet to support itself? What does the armature look like? What does it look like under the skin? It doesn't have skin. Look, one of the big issues with a skeleton is the skeletons are kind of intrinsically scary things. Nobody wants to see their own skeleton. That means you're having a bad day. Skeletons have to be art directed very carefully to look good. If you see Nightmare Before Christmas, you can actually make a grinning skull look happy and cuddly. The biggest thing about skeletons, if you were to look at your neighbor's skeleton, is that you can't really see it because it's inside your neighbor. I have worked in this industry with some people that have some really phenomenal piercings, and still, by and large, you can't see through them. You can see through our puppets, so virtually everything we have to do is going to have to be hidden. And the tricky part is that this is an unprecedented puppet full of an unprecedented armature, and it can't even be built by the puppet department, the people at our facility who have the most experience, more experience than anybody on Earth. See, most of our puppets are small and could be beat up by a large hangry hamster. Even our biggest puppets are the size of a quart of milk, and that's what we're tooled for. Instead of the puppet department, the rigging department, which normally builds the things that have to move out on set, and the set department are going to make this thing. Eventually, it's going to look like this, to give you just some idea of where we're going. Put a pin in that, we're going to come back to it. We have to start from the beginning. Fortunately, we have good data. You know, we've designed everything via CAD and printed it out in 3D and all that kind of stuff. So we have everything that went into the small 3-foot version, which is about this size. They are so cute when they're little, aren't they? And then they grow up and they want to eat your face, and I blame society, really. The original, yeah, it'd be nice if you could just run one out of a 3D printer, but you can't. So we started trying to do it big. The database gets initially run by the art department, and they try to translate it into something that'll work at the scale. The rigging department tries to translate it into something that will stand up at that scale. Tony Chen of the art department and Jerry Swoboda of rigging will together try to hammer out a design. Now, there's a certain dichotomy, natural tension. The art department is using ZBrush, which is a wonderful free-form sculpture tool, and they don't want to change a damn thing in their design because it has been through 37 million layers of approval. The rigging department uses, I believe it's Inventor, which is a CAD system that likes 6 digits of precision, and neither one will talk to each other. So the chain back and forth between the two involves like 3 hops through an old ancient version of Maya, which speaks both languages. If you look at that, there's little 1-foot cubes all over the models that go back and forth, and it's because occasionally things would crash and burn, and like the thing would turn itself inside out. And those cubes were sort of like wisdom on the ground. You could look at those and go, oh no, something's wrong. So eventually, the two of them work together, and they end up with an armature that can actually live inside the bones and not really be seen that much. It sort of articulates like a real skeleton does. And there are some really marvelous little bits of technology that go into it. For instance, if you look at your shoulder joint, you know, it's a ball and socket joint. And we've done those before. I've done ball and socket joints made out of the CV joint for an automobile. It's wonderful. You can transmit torque through it. It's nice and tight, and it's bright, shiny stainless steel. That won't work. So the ball and socket joint these guys came up with, it's brilliant. There's a steel ball at the end of the skeleton shoulder, and then there is a 3D printed plastic cup full of incredibly powerful rare earth magnets that gloms onto that and picks up the structure. So you can actually take the arm and swivel it around like a real arm. The skeleton was just full of this kind of stuff. And so fabrication starts. And it's all this sort of stuff. It's all, you know, the database going in, getting modified, a lot of laser cut parts. Here you can see the rib cage going together. It's a bunch of laser cut parts with some high density foam applied that's then sculpted down to look like ribs. You know, all those carefully planned mechatronic joints have to be fabricated and installed by the riggers. And then what do you do about the bones? even we can't 3D print something that big. And you could think about maybe tiling bones into a smaller print, but you're talking about a lot of weight. It would be really nice if there was like a 3D printer that could print in styrofoam. Well, you know what? There actually is. We looked around and we found a company in Southern California that had these machines that would just take an entire block of HD foam and mill it down to whatever you wanted. Their business was fiberglass molds, but it worked for us. And it turns out, why would anybody need this? It turns out that their killer application is taxidermy. Because in 2017, you don't have to deal with big fiberglass taxidermy cores anymore. If you kill something and you want it in your house, you take pictures of your favorite dead thing next to a ruler and ship the data down to Southern California, and you tell it to, what kind of aggressive pose you want, and you get a foam animal that you can hang the skin on. And that was kind of what we were doing. So we contracted with this company. We sent the data down. A couple of weeks later, we got a stash, several very expensive boxes back that weighed absolutely nothing. Just giant boxes that we had to sign for 65 different ways. And you open them in the floor, and it's comical because just foam beads just come out. And then there's this, you pick up a giant skull, and it weighs like nothing and costs you thousands of dollars. The weird thing is that, and we should note this, bones made of high-density foam kind of have the look and feel and texture of, say, high-density foam. And what we really want is the look and feel of and texture of the bones of 1,000 hapless victims that have been moldering in the crypt for, 1,000 years. So every single inch of the bones had to be covered with an appropriate material. There are a lot of inches on a giant skeleton. And the funny part, if you ever watch it, is that the theme of Kubo is that the boy has magic powers and he can kind of do origami stuff. So a secondary theme of Kubo is the world is largely made of paper. And if you look at our creature here, yes, he's the bones of 1,000 victims, but he's also kind of like, folded grocery bags. You can also, in this shot, this is an interesting shot because if you look, there's a little cavity down under the paintbrush, and that will one day hold a hidden switch that the animator can use to move that joint. So we're going to build the thing, and the question becomes how to move it. Now, when we did Mechadrill, we have all these huge motion control rigs from the golden days of giant miniatures in Hollywood. We went down and we bought them. I think I used this particular machine like 20 years ago to shoot Power Rangers the movie. I know, I'm sorry. And they were originally built to move 100-pound Mitchells around. And so they can carry a Mechadrill. We modified them a little bit. We gave the animators some encoders so they could act live, and that's how we carried the Mechadrills around for our production. This was going to be an entirely different thing, though. A Mechadrill weighs 70 pounds, and we're carrying it around with a 5,000-pound machine. And it was basically just a mass that sort of hung. This skeleton's going to be entirely different. It's going to be projected forward. It's going to weigh 400 pounds. It's got a center of gravity that's way out there. It's got to be manipulated to a much bigger range. Our preliminary calculations showed that a conventional machine was going to weigh about 8,000 pounds and take almost a year to build if we just sort of scaled up conventional rigging. So what do you do? Now, I guarantee that the thoughts that are going through your head are the same that went through mine. Why don't you just use a giant-ass robot? And if this thought didn't go through your head, leave right now, because you are dead inside. Now, this puppy is an ABB 6600 series. This has a 2.5-meter reach. It has a 300-kilo payload. That is a full-size milling machine effectively on the end of that actuator. I love this machine. And the best part about giant-ass robots, they are not as expensive as you think. You can buy these things on eBay. Do we live in a great country or what? Oh, but the problem is, I can't have a giant-ass robot. I would need dedicated power. I would need to rip up a chunk of my stage floor to pour a slab to anchor the thing down. Most importantly, though, giant-ass robots run on their own proprietary PLC controllers, their own control systems that are unrelated to anything. We live in a legacy environment where we're in the middle of an existing tool chain that all our motion control locks in at one end to the animation workstations and at the other end into the data pipeline. And I just can't change it. So sadly, even though I would love my giant robot, my plans for world domination are thwarted once again. So what am I going to do? Well, you know, we've been looking at this technology based on hexapods for Kubo's boat, which gets tossed around in the ocean. Now, for those who have never seen a hexapod work, the classic application is underneath a flight simulator. These are called Stuart platforms, and this has been what they've been used for the past 40, 50 years. Hexapods are not unusual in the film business and visual effects, but usually productions simply rent them from an outside vendor. We didn't want to do that because these are expensive. A small one from Moog costs about $50,000. Plus, we had to build 5 of them. 5 times 50, this starts to add up. Plus, again, it doesn't really integrate with our control system and our legacy pipeline. So we decide we're going to have to build our own. And we've been doing this for the sailboats. And the question is, will this work for the giant skeletons? So, you know, like any good movie, we previs it out. We figure if we make his lair small enough so he doesn't have to step to the side very much, he will just fit. Most of the shots, we don't have to show him from the waist down. The rest of the shots will work, and hence construction begins. Above the waist, the foam bones come together. It's just really sort of amazing how much work goes into something like this. This animation, this time lapse goes about 7 minutes all told, and I can't show it, but it's just phenomenal the amount of effort that goes into these things. Meanwhile, the hexapod fabrication goes apace. This is our high-tech testing department. And eventually it all sort of starts to come together. And the question becomes, well, I've talked a lot about how I can't control things. How can I control things? Now, we are sort of a legacy industry. Things don't move very fast in the animation world. We are very small, and the tools are very, very specialized. And a lot of them have been around a long time. Now, the next slide will frighten people. It will frighten children. If you have children at home, cover their eyes, because I'm going to show you a DOS screen. The one really weird fact is that a lot of industrial robotics actually run on DOS, even today, a lot of new robotics, because DOS is a bulletproof operating system. In a world where the blue screen of death really could be the blue screen of death, you really don't want your operating system to stop in the middle of a move to remind you to, like, update daylight savings time or ask for a new driver. So while DOS and the applications that run on it, this is a motion control system called Cooper, are very, 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 very robust. They are not incredibly advanced, and time has been frozen several years ago. This is the math necessary to make a hexapod work. There is no hexapod module for Cooper. This math makes Cooper sad. So we realized we'd have to do the math as an external process in a second machine. So we wrote a controller for it to calculate the leg lengths, and then we had to patch the two together. We actually do a lot of in-house circuit design and board fabrication and whatnot. And this is an adapter we built so that the Cooper, which is wonderful with encoders and the animators love it, can move master axes that it thinks are actually leg motors. We take that data, it thinks they're actually Cartesian motors. We take that data, we strip out we strip out a correct position from it, we send it over USB to the Mac that we use to actually run the math, and then we send it back and put it back in the Cooper as though it's encoders. The Cooper's running flat out. The Mac is kind of lazing along at 1.7% of its possible workload. But how does an animator control this? We have built a lot of creatures, a lot of things that need to be controlled, and we're big on the Waldo concept. A Waldo, for those who haven't seen it, is a small simulation of a big thing, and you move the small thing, and you've got some encoders on it, and that in turn moves the big thing. In Kubo, we had this creature that in what's called the Garden of Eyes. It's basically a 3-foot ball on a stick, and the Waldo for it we made out of a bowling ball. This has nothing to do with our giant robot. I just like talking about this bowling ball. If you look in the middle, there is a child's trackball, which is the pupil, and then there's a regulation-sized bowling ball which moves the head around on this creature. And the neat thing I did not realize when we first built this, there are two things I didn't realize. There are three things. First, you can buy bowling balls online because you can buy anything online. The concept of bowlingballs.com just really strikes me as weird. Second, bowling balls have serial numbers because bowling ball theft is an issue. But the most important thing about bowling balls, I always imagined a giant blob of plastic, and that is not the case. There's actually a weight inside the bowling ball, so after you drill the holes for the 3 fingers, then it balances. We never drilled the holes. And we didn't realize what this would imply, because every day we went to lunch and we came back and the creature was like this as the bowling ball rolled over on its own weight. And there was a hunt on in the stage for whoever the jerk was who was coming in at lunch and moving our creature. And it took us a good week to figure out that it was doing it on its own. So when we started working on the giant skeleton, we figured we'd do something similar. We'd have a humanoid kind of Waldo that the animator would move around, and that idea immediately went nowhere because the skeleton's up there, and the animator and Waldo are down here, and he's got to keep climbing up a ladder to continuously adjust things. So we went simple. We just put 6 encoders in a box, and that way he could carry it around, and he carried it up the ladder the first time and immediately dropped it. So we put 6 more encoders in a different box, and I have to shout out to one of my engineers who made the big sacrifice. We're looking at how to keep this on our animator's hand, and Dave Trappy runs out to his car and takes the strap off his classic Fender Tweed amp and runs back in and puts it on our box. Godspeed, Dave Trappy. So here's our animator, Charles Green, who had black hair when this started. This is how you control a giant skeleton. You start with Charles, and he picks up the skeleton Waldo, which sends data as encoders into our ancient motion control system, Cooper, which in turn goes through our giant skeleton to Mac adapter, which in turn calculates the actual 6 leg lengths, which goes through all the math. The ugly math goes back through the adapter, goes back through Cooper, goes to the actual legs of the hexapod, and moves the body, the major torso. They should not let me near Keynote, really. They really shouldn't. Now, the interesting thing is because it loops through so many computers, it gives you the ability to catch and replay data, which is really convenient because the first time we went through this, we tried to do the whole thing live, and that was stupid. But we found out that we could rehearse a couple of times. We could catch layers and layers and layers and take maybe the gross body motion and sort of record that off and play that back and layer on top something else that on top of that, because there's actuators throughout this whole thing. Here's a picture of some actuators buried deep in the body that do nothing but shrug the shoulders. We built the thing and we realized that it didn't look alive, which is a dichotomy for a dead monster, but it was still an issue. So we took the whole thing apart and we put in actuators that could shrug the shoulder and move the chest and make it look like it was breathing. And you could build layers of that, so it was like one less thing that the animator, who was constantly climbing up and down, had to deal with. The other biggest issue that I never thought of until we built the thing was the arms. Now, in a standard puppet, the arms will hold themselves. They're small enough. These arms are 9 feet long, and there is no way those joints are holding those arms up. So, of course, we came up with a system of ropes and pulleys up above there to counterweight it and take the weight off. What I didn't realize is that our ceiling is only about 26 feet tall, and we were already up 12, 13, 14 feet next to it. And as the ropes came down from the pulleys, as the arm swung out, the rope came over at an angle, and as soon as you let go of the arm, it wanted to swing back. So if you look very carefully in the sky above this, you'll find these little devices now, which are redirect pulleys. The rope comes off the line comes off the counterweight pulley, it goes through this little redirect device, and then vertically down to the arm. The little redirect device has a tube that the line has to run through, and attached to the back of that tube is a vertical sensor. And there are little tiny microcontrollers in the system that sense the position of that tube and drive wires in an XY plane through these fairly primitive winches to correct the position of that tube so that the last few feet drop cleanly to the arm, and the arm doesn't want to swing when you let it go. So you've got an animator climbing on top of this thing, and he's touching things, and he's moving things, and he's moving cables. And we actually eventually had to make a system of sensitive mats that would, through a variety of mechanisms, detect when he touched the puppet. So what would happen is the animator would walk up, and he'd touch the puppet, and the arm system would unlock, and it would track him as he moved. And then he'd take his hands off the puppet, and everything would lock up. A bunch of the winches would stop moving, and the commands would stop running, and a couple of air cylinders would clamp down on the counterweights, and all the arms would lock up. And I think that's actually the most fascinating part of the whole thing, because we just totally spaced on that to begin with, and had to push that in the last month. Before we shot. Now, I'm talking about things from the waist up, and I don't want to give you the impression that I'm cheating when I talk about the world's largest puppet, because I'm only talking about half of it. We actually do have a set of legs, and we actually do have at least one shot that starts on the tippy toe and ends up at the top of the head. And they actually did live together for one shot, so I'm going to claim this whole height of the puppet. But most of the time, the legs lived on a different set, did shots where the creatures are, the characters are running around the feet. But they do exist. Also, interestingly, even though this is the biggest puppet we've ever used, the scene also contained the smallest puppet we've ever used. Kubo has a sidekick named Hanzo who is made of origami. In our world, Hanzo would be about 6 inches tall. In Kubo's world, Hanzo's about 1 inch tall, but he is fully articulate. I used to carry him around to presentations till somebody dropped him, and he shattered into like a zillion pieces. But he was fully articulate before he died. I'm going to play a clip of video to give you some idea of how big this thing was. This was a bumper that we used at the end of the show.
Look at you all. See the love there that's sleeping, while my guitar gently weeps. Look at you all.
And then it kills Charles. You know, despite all his rage, though, he is still a skeleton in a green screen cage, and he's got to be in an environment. As you might imagine, a lot of our environment is CG. We shot the feet and all that stuff on a practical stage just because we have real puppets. And we incorporated a belt line into the set to give us a clean break to the CG half. The set itself is sort of based on the Celdeck ossuary in Portugal. It's just, you know, halls and halls of bones. And the nice thing about lots of bones is that they tend to be repetitive and, you know, pile of bones, it sort of looks the same from every angle. So that did cut down the work time and the modeling time. We had a bunch of primitives that we sort of tiled and moved around. You know, this is sort of the standard tricks. One issue, though, is that the material we chose for the Hall of Bones is supposed to be jade. And jade is really interesting because it's a very 3D material. There are translucent parts of it, there are transparent parts of it, there's a lot of diffraction, there are veins of minerals, blah, 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 blah. We could build them in the real world. Our set designers could build them by taking various types of epoxy resins, and they'd do a layer and they'd paint some minerals in it, or they'd toss some talc in it and they'd do another layer. But it was really, really difficult doing it in CG. Our shader team worked on this for a long time, and they ended up with a material that was really, really good. I mean, it's an excellent match, but it was insanely computationally intensive. These little bits and pieces are the most computationally intensive thing we've ever done, and we have done large crowd scenes. This is a quote from Eric Walkman. He's the head of our shader department. This is apparently English. I don't really know what it means, but it got a big round of applause at SIGGRAPH, so there you go. If you are into shaders, we have moved to a new thing we're working, and we've put our old plausible shader, the one we used for this, we put it up on the RenderMan community page. So if you want to do your own jade, you can actually load down the stuff we actually did and use it. Now, this is not so critical in the Hall of Bones, but one of our biggest CG challenges in these extended worlds is the fact that we're extending a puppet world. It's not CG, there are tools for that. It's not real world, there are materials for that. It's sort of a weird thing that's its own, that's somewhere in between. It tends to be like a lot of weird textures, but textures that nobody else has to use, and textures that don't really flow from the CG world. It's very highly stylized, and it has to match. So we do, oops, I actually had a demo of that, and I didn't use it, I'm sorry. So we do a huge amount of photogrammetry to make sure things go together right. We sort of have the advantage that our world moves slow, and we can get surveying tools in and photogrammetric tools in, do like a big HDR pass around our sets and create an artificial lighting world that we can simply wrap around our CG sets. And a lot of that is sort of what we've done with Hall of Bones. It's just layers and layers and layers. And this is sort of an initial look dev of what that looks like. Again, practical on the bottom where Monkey is actually touching it, and a CG extension. And I think the materials match pretty well. Now, that's about how we built our giant skeleton. Would I do things differently? Oh yeah. I didn't realize how difficult it was going to be to do this. You know, how difficult it is to access such a huge thing. You're up and down on a ladder, and ladders are dangerous, and we had some slips and falls, so then we went to scaffolding. And scaffolding is great. It's much more efficient, it's much safer, but it grows like kudzu in the Georgia sun. You have a little piece of it, and then you have another little piece of it, and then you have a railing, and then you have this, and you have that. And we had to keep digging our skeleton out from the scaffolding as we moved the camera around. If I were doing it again, I might actually use the giant ass robot. I might bite the bullet and pour the slab. I might actually just dig a hole in the ground and bury the hexapod down to sort of waist level. But I might use the giant robot because really it'd be, it'd be a little more efficient and, a huge, thinking machine full of giant servos. What could possibly go wrong? Anybody want to see the final sequence and see what an entire year and a couple of $1 million will buy you? Yes. Play now.
No. Yes.
Matthew McConaughey, he is hilarious.
Kubo, look.
Is the sword unbreakable?
It could be a trap.
Allow me.
What? It's not a trap if you do it?
Stealth is my middle name.
You don't even have a first name.
Don't worry, I got this. The mighty beetle is victorious!
To me, this seems like a really good time to run away.
I don't got this. I don't got this!
Oh, for crying out loud! I invoke the sword unbreakable! It broke.
So, does it just mean the handle, or...? I'm a little disappointed with this magic sword.
It's not the right sword, you idiot! Look!
The sword!
It's in his head!
Hey! I've got a bone to pick with you. See, because he's made of bones.
You're an embarrassment.
This is problematic.
Enough with the arrows! You can fly?
Apparently, yes! Are you sure it isn't the sword unfindable? I think I found it. A hand here. Anyone? Anyone else?
Kubo!
Thank goodness that's over.
And that's it. There's a really fine line between inspiration and insanity. And it runs like right through Studio Blue 6 in Hillsborough. And that's about the end of the show. I guess we really don't have much time. We'll jump to questions. Does anybody have questions, or? All right, we do have time. We've got, what, about 5 minutes? Somebody in the back? Oh.
Hello? Oh, okay. So, in the end, when the skeleton crumbled, it actually, like, I assume in real life it didn't fall apart. How'd you get that to...
That's our 3-foot skeleton crumbling. That is the one shot. The question was, when the skeleton crumbles at the end, how did we do it? I think there are like 3 or 4 shots that survived on the 3-foot skeleton, and that was one of them. So, nobody else? Okay. Then I'm going to riff for about 5 minutes. Yes?
The actuators, is that what they're called to help with the movement? Or what were they called?
Yeah, the legs are, the actuator is the right word for the device that moves the legs.
Because did you guys use that in Missing Link too? Like to help them breathe and move?
Oh, yes, very much so. In fact, the puppets have these little things inside of them now. We call them jetpacks. They fit inside the back. And, a couple of bicycle-type cables come out, and by twisting them, the puppets actually have chest heave and all this. It's really quite fascinating. I didn't bring anything about that. Anybody else? Oh. Yell it.
So I saw like that on the pulleys and all the machines, there was like green for the green screen to cover it, but on some of the wires and ropes there weren't. So
Oh, no, the wires and ropes are just aircraft cable. The question is, how do you get the wires and ropes out? The illustration I showed, the wires and ropes are not brightly colored. We just colored it in to give you an idea of where they were, because otherwise they're difficult to see. We buy aircraft cable in bulk, and we send it to a chemical plating company that makes it into a very dull gray, and it sort of just disappears. It's really easier making it disappear than it is to try to key it out. Yes? Well, by and large, since we have motion control equipment on all the stages running all the cameras, once we get a move, we can move it across the various stages. And for the move where we shoot on one and end up all the way on the top, we actually had 2 shots. I don't know if you saw them go by. One is a real practical shot where we swoop up and we simply arrange the shot so that the point of view jumps from the knee over this area of the thigh and into the torso, so you don't see all the machinery. The knee blocks you as you're coming up, so you don't see all the peripheral machinery. For some of the other shots, we simply did match moves on two stages because it was easier. And we could move the legs over to match, but we didn't really want to move the whole floor. So, anybody else?
Back here?
Yes.
How long did it take to make that scene with the skeleton?
The better part of 2 years. From initial, I went back and I looked at some of the timestamps on the pictures, and I think some of the earliest pictures the earliest pictures date to late 2015, early 2016. So then somewhere around 2 years, end to end. So. Animation is not a fast game, I assure you. Yes?
So while you guys were working on the skeleton, there were other people working on other scenes?
Yes. Our facility is about 320 feet on a side. It's the shooting stage is roughly 320 feet square. I think I worked it out once. It's something like 4 1/4 acres. and it's subdivided into a bunch of sets. The biggest, we've got about a 26 to 28 foot ceiling, and it's subdivided by hanging black drapes. The biggest of the sets is about twice what we have in here. The biggest of the stages is about twice what we have in here. The small insert stages might be 10 by 10. We have, depending on how you count, somewhere around 90 stages. And we will duplicate a set. We'll have like 5, 6, 8 copies of everything because it takes so long to shoot a scene, shoot a shot, that if we did them end to end, we'd never finish a movie. As it is, we barely finish our movies. So yeah, we'll often have 3 or 4 different, corners of a set and maybe a master set, and just work everything in parallel. It's actually our biggest schedule issue, is that in order to get all these sets working in parallel, you need spare puppets. You might have 8 or 10 hero puppets for one character, and the fabrication of the puppets is insanely time consuming, especially something like Monkey or Link, where we have fur. Fur just takes forever.
All right, guys, I think we have time for just one more question. I'm actually going to hand this over to Kendall, who's been sitting on this one, and we will then wrap up.
So my question is, you talked a little bit about the pre-production. What other pre-production did you do up to the process where you started building so you knew what you had to build?
Well, the question was about pre-production, and animation is actually really unique. I know a lot of you guys work in visual effects or post sound, and the issue in visual effects and post sound is always that things change up to the last minute, and then the VFX guys get all these additional shots at the last minute, and they do their thing and deliver it to the post sound people with like 38 seconds to go before you have to lock the negative, and then the post sound people have to work around that. None of that happens in animation. Animation is Eden for post-production people, because we have to do it all ahead of time. If you think about a shot in a normal movie where people might be driving a car or eating dinner in a restaurant, in the real world, you can just go rent a restaurant for a morning, bring your crew in, sit your people at a table. If you need forks, they have them. If you need food, it's down at Publix. We don't have any of that. If there's a prop that we need, it has to exist, or we wait. So, and animation is very painfully slow. So if you have dialogue or you have gestures, you really don't want to shoot anything spare. When we shoot handles on our animation, we shoot 6 frames. So the first thing we do is do the dialogue and cut it together with storyboards for pacing and people interrupting each other and all that sort of stuff. And more storyboards, and then more storyboards, and then we'll start building sets and stand-in sets and stand-in puppets, and we'll shoot temp stills and whatnot. We'll start cutting them into the storyboards and more storyboards, and we'll eventually have a cut that's nothing but audio and storyboard, and it becomes a Bible, and we will make exactly that on the set. And that whole process takes as long as a normal movie because it's making a normal movie. And when we get turned loose on the set, it takes us a long time, but all we do is assemble what we already need. What we already know we need. It's tedious, but it's very straightforward. It's really kind of weird because it happens exactly opposite. There we go.
All right, guys, thank you so much for joining us today. If we can give our presenter just one final round of applause. Thank you so much for an informative talk.